Mark, welcome to Talk Satellite here in Washington, D.C.
Pleasure to be here.
What would you say are some of the key elements of the future of MILSATCOM architecture that enable adaptable systems and blended networks?
Well, there are quite a few that the military is interested in. The top three would be able to use multi-orbit constellations. And the reason for that is capacity, to get the capacity, also to get the resilience, be able to go over one capacity, one type of satellite or not, because the government worries about denial of service, one service not being available for a variety of reasons. They want to be able to utilize the new LEO constellations, but also the existing emerging MEO constellations and their legacy GEO constellations that they own, things like WGS and so on. So it's going to be a blend of all of those things, and they want to be able to adaptively use those. One of the things that helps them do that is the next generation digital ground architecture. So that would be another key element of their future generations, to be able to digitally distribute signals, process them, and so on to enable using of those architectures. And I think finally, they want to have a way to be able to easily use those. Historically, the old SATCOM systems were very hard to configure and use. And so they're really looking at some new ways to be able to make that be much more of a user-friendly kind of experience. The configuration element of that is the burden has been.
What is a digital ground architecture, and what is the advantages and where we are at deploying these?
Digital ground architecture at its heart is simply digitizing either RF or lower intermediate frequency signals and be able to distribute around and process them efficiently. Maybe it's easiest to understand what the current system is, the legacy analog distribution system. What happens is signals are received and transmitted from an antenna at the radio frequencies. These are the higher frequencies of X band or K band, whatever band people are using. And they're transmitted to a lower frequency, and then in the analog world, a lower intermediate frequency. And then in analog form, they're switched and signaled around by splitters and switches and so on. It works fine, and that's what the legacy system works. It's just that it has limitations. For example, there's only so far away that you can be from antennas. You're limited to how many modems that you can easily distribute these things and so on. New digital ground architecture, those signals, either at the RF or later further down at the IF, are sampled and then distributed via Ethernet networks. And just like Ethernet networks that there's a lot of advantages to that. There's flexibility. You can now distribute things much more effectively, and it's superior to the analog world and all of the parts of the acronym of SWaP-C, which stands for size, weight, and power and cost. And so it's lower size, it's lower weight and power. It's also a much lower cost way of doing things. It has other advantages of just higher performance. There's a lot of degradations that happen when you distribute signals, in an analog way that now you do much more with much higher performance in a digital world. Perhaps most effectively, or most importantly, there's a lot of flexibility now that you can easily distribute signals, for say, within a local network to multiple antennas, to multiple polarizations, multiple bands. You can distribute over a wide area network to another gateway. For example, if one gateway is having a problem, you can now shift those signals to another gateway and utilize that gateway. So a lot of resilience benefits. And then even further, there's advanced signal processing that can be done. So now I can do spectrum monitoring, I can do phase combining, interference cancellation or detection, signal analysis, and so on. A lot of other things are possible because I have easy access to those sampled data, and now I can process them much more easily than I've had analog data. So it's just a superior way of doing it, and I think it's maybe either controversial or uncontroversial to say, but I think, if we look forward 5 or 10 years, I think the analog way of distributing signals will no longer be used, and the digital equivalent of this will be.
So Comtech has recently delivered its first set of EDIM modems to the US Army. Can you run through this milestone for us?
Yes, the EDIM or the EDIM, it stands for Digital IF Multi-Carrier Modem. So that's a 1RU platform. It has 8 different modems in it. It supports both legacy government waveforms and the newer open standard DVB-S2X waveforms. So it interoperates with government and commercial type of networks. And then it has, as the name suggests, the digital IF. It has digital IF interfaces to support the new next generation digital ground architecture, which the government is planning on implementing. It's one of the first products now that's designed from the very start to support that architecture.
How do you see technology playing a role in a broader spectrum for the end user?
Well, we've certainly seen a lot of technology, and it's been a very exciting time in the satellite world over the past 2 years. We've seen a lot of technology from LEO providers coming in and giving vertically integrated solutions that lower latency, increase data rate, increase the user experience. Seen a lot of that same kind of thing now with the legacy systems catching up to that sort of. There's a lot of technology being applied. I described some of them and be able to use multiple of these orbits and use a digital ground architecture to gain some of these advantages. So there'll be no end of those kind of technologies providing those benefits in the future. So after the satellite industry, after being very sort of staid and conservative for a long time, is now entered this growth phase where a lot of technology is being inserted, and there's no reason to believe that won't continue for some time.
Mark, thank you very much indeed for coming along today.
Thank you. Thank you for the time.